From this lecture onwards, we will start the construction of the transformer. The principal components of the transformer can be classified as magnetic circuit, electric circuit, and tank. Magnetic circuit mainly comprises of transformer core having limbs and yokes. Electric circuit mainly comprises of windings, insulation, and bushings. Tank mainly comprises of cooling devices, conservator, and ancillary apparatus. The construction of a transformer depends largely on its size and the duty. The main component of the magnetic circuit of the transformer is the transformer core. Now, let's see the construction of the transformer core. A transformer core serves the following three important purposes. It provides the mechanical support to the windings, provides a low reluctance closed ferromagnetic path to the magnetic flux. It reduces the losses due to the flux leakage. The primary and the secondary windings of a transformer are wound over the core but physically separated from each other. The transformer core is designed to magnetically link the windings and also to provide low reluctance path for the magnetic field. The core must be designed in such a way to minimize the eddy current losses and the hysteresis losses. On the contrast, the core acts as a coupling device between the windings. For the construction of the core, at first we need to choose the core material. The following factor affects the selection of the core material: maximum magnetic induction, minimum specific core loss for low no-load loss, low reluctance to magnetic flux, low apparent power input, low magnetostriction for minimal noise, good mechanical strength to hold the windings. Let's see the material for the construction of the core. The core is made of sheets of alloy steel. Main constituents of the alloy steel are silicon and carbon. Silicon and carbon increases the permeability at low flux densities and also reduces hysteresis loss to a large extent. And with the use of silicon, the resistivity of the core is increased, so eddy current loss is reduced. A special type of sheet made of material known as CRGOS or cold rolled grain oriented steel are used for the core construction. Because this material has excellent magnetic properties in the direction of rolling, the flux density is very high. Now, for the construction part, we need to focus on a very important factor for the transformer, and that is reducing the eddy current loss. In order to reduce the eddy current loss, the core of the transformer is laminated. The lamination of the transformer core is made of cold rolled grain oriented steel at a thickness ranging between 0.18 mm and 0.35 mm. Since the eddy current losses are proportional to the square of the thickness of lamination and the frequency of the alternating current, thinner sheets are always preferred for core construction. So every effort is made to reduce their thickness and to make the thickness as small as possible. But there is a practical limit beyond which the thickness of the lamination cannot be decreased further on the account of mechanical consideration. The practical limit of thickness of each lamination is 0.3 mm. The lamination are usually made of 0.33 to 0.5 mm. On the other hand, reducing the thickness of sheets degrades the stacking factor. Deburring the sheets and annealing them at 800 to 900 degrees Celsius in natural gas environment improves the stacking factor and minimizes the eddy current losses. The laminations are generally passed through hot steel slabs that squeezes them to thin sheets, and also both sides of the sheets are coated with carlite, which is a thin layer of oxide coating or varnish in order to insulate them from adjacent sheets. Core cross section. Smaller transformers have rectangular section limbs with the rectangular coils or square section limbs with circular coils. As the size of the transformer increases, it is not efficient to use the rectangular cores. For this purpose, the cores are square shaped, which is shown in the figure. The circle denotes the inner surface of the tubular former that houses the windings, and the circle is referred to as the circumscribing circle. Clearly, a lot of useful space is being wasted as the circumference of the circumscribing circle is long in comparison to its cross section. That means that the length of the mean turn of the winding is increased, giving rise to higher I square R losses and conductor cost. The circular coils are preferred for winding a transformer as they can be easily wound on machines on a former. The conductors can be easily bent and winding does not bulge out due to the radial forces developed during the operation. This means that the mean turn length of the winding is increased, resulting in higher I square R losses and conductor cost. The circular coils are favored for winding a transformer because they can be easily wound quickly on a machines on a former and can be bent easily, and the winding losses does not bulge out owing to the radial forces developed during the operation. With larger transformers, cruciform cores which utilize the space better are used. The cross section of the transformers is a cruciform core is shown in this figure. Here, the space utilization is better with the cruciform cores, and the diameter of the circumscribing circle is smaller than with the square cores of the same area. Thus, the length of the mean turn of the copper is reduced with the consequent reduction in the cost of copper. It should be kept in mind that two different sizes of the lamination are used in the cruciform cores. With larger transformer, further steps are introduced to utilize the core space, which reduces the length of the mean turn with the consequent reduction in both the cost of copper and copper loss. By increasing the number of steps, area of the circumscribing circle is more effectively utilized and the most economical dimension for a multi-step core can be calculated. Lamination of the core and the insulation between the lamination have the effect of reducing the effective or net area of the core. The net core cross section is about 10% less than the gross sectional area due to the lamination of the core and insulation such as paper or varnish. The ratio of the net cross section area to gross cross section area is called iron space factor or simply iron factor Ki. So Ki is equal to Ai divided by AGC, where Ai is the iron area or iron's net cross section area of the core and AGC is the overall area or gross cross sectional area of the core. Ki is less than unity and it is nearly equal to 0.9 to 0.99. That's all for this lecture. If you have any doubts regarding this lecture, then you may ask it in the comment section, and don't forget to hit the subscribe button, and see you in the next one.